Welcome to the ValveStudio. Our work on this Mectron Record Player continues. We're going to go ahead and pick up where we left off. Just a little review. We've gone through and we did the complete biasing. We determined the bias point and we measured it. We were pretty close. Then the last time I looked at the, I used my Jupyter notebook to look at the performance of this output tube running as a triode. And today we're going to cover the Pentode, but let me give you a little bit of review. This is a record player I bought at a thrift store for about $20. It's a 3-tube design. It's got a half-wave rectifier, which is going to introduce some noise. It's going to make our measurements here on the bench a little bit of a challenge. We'll work on that in future episodes. It has a 12SQ7, which is a high mu triode. It's a preamp, and it feeds that right into a 50L6, which is the output tube. And there's only one of them, so it's a single-ended design. I went ahead and measured the turns ratio on the transformer at 33, and I'm using a Celestron 4-ohm 8-inch speaker for this design. So it's just it's a brief introduction. You can go back and look at some of the previous videos on this Mectron, but we're going to talk about the Pentode performance today. So I have the Mectron Record Player schematic open here in my Jupyter notebook. And remember, this is the Tube 2 design. It's got a half-wave rectifier. And this turns ratio here is 33. And I'm running a 4-ohm speaker, and this is the bias point that we found. And I'm just going to quickly go over the performance of the triode when we're running the triode mode. So here's the plate characteristic for triode. We went ahead and extracted out all that data using NQ. And anyway, here's a bunch of Python code. We get down here to our analysis component here. This is the part here where we can actually move the load line around. And if you watch the last video, we determined that we can go place this load line, but this is actually where the design actually sits. And because the slope of this line is based on the turns ratio and the output transformer, the reflected impedance back into the plate circuit results in this resistance here. Because of that, down here at the transfer characteristic, we get this particular transfer characteristic, where here's the grid voltage that we apply, and then here's the plate current that we're going to get back out again. And so when we superimpose an AC signal onto our Q point here, our bias point, we're going to swing around this area of the transfer characteristic. We can't go above 0 because then we'd have a grid current, and the circuit doesn't support kind of any grid current, the driver for this output tube. All right, and when we're running it down at this level, we end up getting, I think we found that we end up getting about, we get about, I think it was about 400 milliwatts of power at about 5% distortion. So keep that in mind. As a triode, we're getting at less than half a watt at 5%. So let's move on to the Pentode version of this, which is where I've got it wired back up again. Same as circuit. We're just using it in Pentode mode now. All right. So here's this is the plate characteristic for a Pentode, and we're using the GE here for a 25L6, which is the same as a 50L6. It just has a different filament voltage. So again, I went in and I extracted out the data using NQ, and I have the similar type of graph down here. We get back over to our load line tool in the section of the notebook, which is right here, and let me rerun all these cells so it puts back my default values. So it's rerunning all the cells, and so here's the actual Q point with the load line. We're at 124.8 volts for the plate voltage, and we're at 47 milliamps of current. And so we swing around this point when we're actually in operation. Now let's look at with this load line at this position. This is based on the fact that that we have a 4 ohm speaker, and I'm using a resistive impedance at this point. We'll talk a little bit more about what happens when you actually want to model this with a speaker load, but we'll handle that in the future. Not today. We'll just keep it simple at 4 ohm resistive impedance transferred back in through the turns ratio back to the primary results in this AC load line, which is equivalent to 4.35 k ohms. All right, so now let's move on to the transfer characteristic. One thing I want to show you up here is, okay, so as we get to this area over here, which is the saturation point for the tube, our anode current, our plate current goes down for increasing values of gate voltage or grid voltage. I'm sorry. And the other thing to notice is the spacing between these actual points here gets narrower and narrower as we reach cutoff. So what is that actually going to look like when we plot this on the transfer characteristic? This is an interesting thing to think about. These are smashed together, as well as the distance here between these points is smashed together. And that actually is quite pronounced in this transfer characteristic. So here's the characteristic. This is just a different graph. This is actually a graph of the it's this data from the other graph, but it's showing you the grid voltage on the x-axis and the plate current on the y-axis. So as the voltage gets lower and lower, we get to a point where we don't really see that much change in the plate current. And this area up here is what happens to this when we start operating up in this region, because we're going more and more positive. So our grid voltage is going almost to zero, which is what this top line is. We don't see that much change. So these 3 points are these 3 points on the graph. So if we swing up to this point, we eventually start hitting we hit a saturation point, and this is what ends up happening. Then down here, what happens is these 3 points are a result of this distance here being smaller. So as these get crunched together, we end up having a nonlinear characteristic in the transfer curve down here as well. So if we want to look purely at the voltage swings when we're kind of in a linear region, we really are limited to -4 up to 12. And then if we get anywhere more positive between -4 and 0, we hit this one here, and we also are going to go over here. So that's going to have an interesting look when we look at the transient response down below. So if we zoom down here with those particular values, here's our transient response. Here is our drive signal, and we're sitting at the operating point of -8. And this is what our output voltage is going to look like. So now let me raise this up. We're at 1 volt. At 1 volt amplitude here, so we're going up to 7, down to 9, and this one goes down to about 90 and up to about 160. So that means that on this curve, we're doing 1 volt excitation. We're going from here, this is our operating point, we go up to here, and we go back down to here. This is kind of where we're swinging at 1 volt swing. And on this curve here, that's equivalent to, we're moving from here up 1 volt. So there's a curve in here that you don't see, but we're actually running right around in here. So you see 1 volt change from here, it goes up to about here, which is about 90, and we go back down here about 1 volt, and we are back around 150. So we're swinging in this area right here with a 1 volt excitation. All right, that's That's what we have here. Now this is the harmonic content right here. I actually, of this waveform right here, I did an FFT, and this is the log plot of that result. So we're at 29 dB for our fundamental. And here's our second harmonic. It's 40 dB down. And here's a third harmonic that's even farther down. This one is probably at, was that about minus 22 or something. So this is about 30 dB down. About 50, I'm sorry. So almost 50 dB down is the third harmonic. So this results in a distortion figure of we got 1 watt out at 0.1% distortion. So let's turn up our amplitude here. Let's turn it up so that we just get to this point here. So if we're at minus 8 and we want to go to minus 4, we got to have our amplitude at 4. So we'll come back down here and we'll crank this up to 4. And then it'll go redo our analysis. So if we go up to 4 volts, we get 6 watts output at 1% distortion. And what you're seeing down here, okay, this is the output waveform. You're seeing a visual distortion of the output waveform, but we're only at 1% distortion. And you see that this is starting to get flatter. That's because as the voltage gets more and more positive, we're going from minus 8 up to 0. This is that point where we start hitting that plateau on the right-hand side of the curve, the transfer curve. So we're not going to see that much output current coming out. And that's what results in this flattening down on this side. So if we come back up here, what we're doing is we're approaching this area of the graph, and we're going to see a flattening because there's not much change in the plate current at that point. That's why this flattens out right here. And this one gets distorted as well. Not so pronounced as this one. This area here is when our grid voltage gets more and more negative. So we're reaching cutoff. And so on this graph, we're back down in this area right here. All right, but that's still fine. If we actually want to look at the theoretical numbers, we're at 6 watts now at 1% distortion. And here's what the frequency response, or the frequency analysis of the FFT of this output wave. We're at 40 dB now, and our second harmonic is 13 dB down, so we're at 27 dB difference between these two. But look at the third harmonic. It's actually come up quite a bit. It's actually at the same level. And we're getting a little tiny bit of the fourth, and we're getting more of the fifth. All right, so we're raising our harmonic content up, a little bit. We're still down at 1%. Let's go even higher. Let's go back up to, where should we go on this graph here? Let's go back up to, let's go to 0, and that would mean we need to make this, let's make it about 7.5 our swing. So we're going to run up to this area, and we're going to run back down to this area down here. And let's look at what the output waveform, what we should expect to see if we make this 7.5. So 7.5 is going to be right about there. This thing takes a little bit to get caught up. All right, so we're at 7.5, so we're almost exact. We are just barely getting to 0. We don't want to positively bias the grid. And then here's what our output waveform looks like now. We're at 16 watts at 2% distortion, at 3% distortion. And our harmonic content has really grown quite a bit. So our peak difference here is at 20 dB from our fundamental to our second. Our third is still the same. We're getting a lot more fourth and actually a lot more fifth. All right, so this is the kind of the performance of the amplifier at the current operating point, which is right here. Let's go back up to this point. Now, how do we improve this? How do we make these dots further apart so that they're more like this distance here? It's a good question. Well, the answer to that is we can move the operating point. We can't really, this line here is a function of the power. The maximum plate dissipation is 10 watts. So we can operate down here as a safe operating region. So what I ended up doing was I kind of came up here and tweaked my sliders. So I tweaked my sliders, and I kicked this guy up to 60 milliamps for the plate current, and I set my my plate voltage at 160. And then I'm kind of stuck with a 4-ohm speaker, but say that I wanted to completely optimize this design. I found out that if I make my turns ratio down 25, my turns ratio of 25, what that effectively does is change. Am I sitting at the right? No, I'm not quite at the right spot here. Let's. I had this up to 5. I had this up to 5 watts. Well, that's interesting. All right, let's play around a little bit here. That's interesting. Was that? Oh, this needs to be 165. Okay, here we go. And this was 25. All right. So I played with my sliders, and I kind of moved my point around, and I changed the slope of this line. And now I'm getting out 5 watts, and my turns ratio is 25. So the plate actually sees 2,500 ohms. So let's go look at the impact of that on our curves down below. So we need to go in this cell and re-execute it. Now here's our transfer curve for a new load line. You can see that this region over here is dramatically different. It doesn't have that plateau in it. The reason for this is that this area over here, these last 3 points, are actually a lot farther apart. These two are not quite far enough. That's why we're getting a little bit of a slope change on the transfer curve. So the Valve Wizard says if you want the highest performance on your amplifier, when you pick your load line slope, you want to be just below the knee. Okay, so we want to be right around in there. I'm not going to fool with that today, but there's you could tweak the turns ratio a little bit more and get this to sit up here. And then the distance from this point to here will be about the same as this one, and this one, and this one, and this one. Now you're still stuck with the distances here. So you're still going to have an issue on the load line down when your grid voltage gets more and more closer to cutoff. But that's okay. So let's go look at the thing here. Let's go look at the power output here. So we're at -6, so we can pretty much go up to, about 5 volt swing here, and pretty running this linear operation here. I'm going to come down to this cell, and I'll re-execute this cell so we get our new graph. All right, so if we're at 1 volt excitation, we get 1.5 watts out now at 0.1% distortion, and here's our harmonic content. So let's go back up to 4 like we did before. Not to 7. Let's go up to 4 here. We got to wait for this one to get to 4. Okay, so we're getting 5 watts out at 1% distortion, which is pretty good. You can see here now this is a different profile of the harmonic content. Remember before, when we were at this point, we barely had a little bit of fourth, but now we have a lot more fourth. But we have less fifth harmonic. So our harmonic content is different, and our output graph looks a lot different. We're not near this cutoff, that region down here just yet. So we're getting 5 watts out at 1% distortion. And this distortion is actually probably pretty pleasable to your ears, because it has, this content is the even harmonic, and the odd harmonic is still down by 40 dB, so this isn't really going to affect anything. So that's the impact of selecting your load line based on the turns ratio. And an optimal design for power output, if you're only interested in power output, you do want to pick your operating point either somewhere below your maximum power output of the power dissipation limit. And if you go on the other side of this, there's some impact to the life of the tube. But if you stay on this side, you have a pretty good life of the tube. And by changing this slope, you can dramatically affect the output power as well as the audio performance. So I'll wrap it up here. This is on my GitHub page. If you want to download this notebook, it is this notebook is called let's just go back here. This notebook is called the Mectron Loadline Pentode, and I encourage you to go ahead and download this and run it in your own notebook and play around with these things just like I did today. Well, that wraps it up for today. Thanks for watching. This is the ValveStudio.